everybody. Thank you for coming to this lecture. My name is Mateusz, and I'm going to present to you some introduction to tropical geometry. So in order to do that, let me start by telling you roughly what is tropical geometry, and then why am I talking about tropical geometry at this launch. So here are two quotes about tropical geometry. The first quote says that tropical algebraic geometry is the geometry of the tropical scenery. Its objects are polyhedral self-complexes, which behave complex algebraic. And the second quote says that tropical geometry is a combinatorial shadow of algebraic geometry, offering new polyhedral tools to compute invariants of algebra. Okay, so I think that these two quotes characterize two aspects of tropical geometry. So the first aspect of tropical geometry is that the tropical geometry is supposed to be some kind of an analog of algebraic geometry over this thing that is called the tropical scenery. And the second quote claims that tropical geometry has some connection to the standard algebraic geometry, and that it is some sort of a combinatorial shadow of algebraic geometry, which may sound very mysterious when you hear this for the first time, right? So my aims for this lecture is to basically explain these two things. Namely, I will tell you how can we meaningfully define an analog of algebraic geometry over a structure that is not a field and not even a ring, a tropical scenery. And secondly, I would like to tell you how this study of this tropical geometry relates to classical algebraic geometry. Okay. And now let me explain why I'm giving this talk at this workshop. So this is because tropical geometry appears as a part of the PhD topic of GC3 of Sami Halasek, who is working in Kubernetes between Toulouse and Constance. And as part of his PhD project, we are planning to investigate whether the tools of tropical geometry can be used for some topics that are interesting to the tenors network, such that like the moment relaxations in polynomial optimization and or the tensor composition. Okay, so I think that some of you have not been really exposed to tropical geometry before, and some of you maybe have never even heard about tropical geometry. So I prepared this lecture especially for these people, right? So the lecture is super basic. We will start from zero and build from there. So in particular, I will not go into applications of tropical geometry to, let's say, optimization problems. I will focus on the results that are by now very classical tropical geometry. So this lecture is going to have roughly two parts corresponding to today and tomorrow. So today, I want to introduce the basic notions of tropical geometry. So we will talk about the tropical scenery, we'll talk about properties, then I will introduce tropical polynomials and show how they relate to regular subdivisions of Newton polytopes. And in the second part, so roughly tomorrow, we will see some connections between tropical geometry and algebraic geometry. So we will talk about tropical hypersurface, subhypersurfaces, about Guizot series, and then I will present a few basic theorems, Kaplanov theorem, fundamental theorem of tropical geometry, and we will finish by discussing the amoebas and the roots. Okay, so this is supposed to be interactive. So if you have any questions, ask me questions, and I will also ask you questions. Okay. So if that's fine, then let me present to you the two main actors. Oh, sorry. Yes, so I have also this slide. So I prepared this lecture using some materials from these four books. So if you want to know more about tropical geometry, I highly encourage you to check them out. So these four books are quite different from each other, and they cover a lot of different topics, but together they give a great overview of tropical algebra and tropical geometry. Okay, So now let me present to you our main actor, or rather our main two actors, namely the max plus semi-ring and the min plus semi. So the semi-ring is, as the name suggests, an algebraic structure that is supposed to be like a ring, right? So in particular, in this algebraic structure, we will have two operations, one that we will call addition and one that we will call multiplication. So in the case of the max plus semi-ring, our ground set is going to be real numbers together with minus infinity. And our addition will be the standard maximization between two numbers. And our multiplication will be the standard addition between the two numbers. Okay? And in the min plus semi-ring, well, it's very similar. So I get the real numbers, but this time plus infinity instead of minus infinity. And the addition will be the minimization instead of maximization. Okay? So let us look at some examples to familiarize ourselves. Okay, so suppose that I am in the max plus semi. So what is 2 plus 3 in the max plus semi? Well, the addition is maximization, right? So 2 plus 3 is 3 because 3 is the maximum between 2 and 3. So what is 2 times 3? Well, that is supposed to be the addition, standard addition. 2 plus 3 is 5, right? So that's 5. So now if I take minus 11 plus minus 6, entropically, I get minus 6, because minus 6 is higher than minus 11. And then I multiply these two guys, I get minus 17, because that's the standard addition, right? Okay. So let us now remark that this minus infinity of this max plus semi is actually the neutral element of addition, right? Because the maximum between minus infinity and a is a. So that's the neutral element of addition. And 0 is the neutral element of multiplication. Because 0 times a is 0 plus a. And we can also remark that the addition in the semi-rings is idempotent, meaning that for every a, we have a plus a equals to a, right? Because this is just the maximum a. Okay, so I hope that these basic operations are fine for you. Okay, so here is the first exercise for you. So what is exponentiation? So if I take an element of my max plus semi-ring and I raise it to the power k, what do I get? Yes, that will be the multiplication by the exponent, by k, right? So a to the power k is a times a blah blah blah, which is a blah blah, which is k, right? So now what happens in the higher range? So now I take a vector and I take a multi-index, and I take a vector and raise it to the multi-index, like in the standard notation, right? Yes? Sorry?
Dot product.
Yes, it's an inner product, exactly, yes. So that's the scalar product, right? So x to the power alpha is x1 alpha 1 times blah blah times xn alpha n, which is the scalar product. Yes. Okay, good. So now we know how to do the exponential. Right. So now let us discuss some properties of this segment. So now let me claim that the max plus and min plus semi-rings are, despite their name, they are actually semi-fields. Right? So what is a semi-field? Well, semi-field is a structure that satisfies all the axioms of fields, except for the existence of subtraction. And the exercise for you is to prove this. Right, so let me recall that, well, there are 9 axioms of fields, right? So, and we claim that this satisfy 8 of them. Okay? So the first four axioms are the associativity and commutativity of addition and multiplication. Right? So here I hope that there is nothing to prove, right? The maximum of A and B is the same as maximum of B and A. So that's fine. Then we have additive and multiplicative identity, but that we have just seen, right? It's minus infinity and 0. So that's fine. Then we have the additive inverse, right? So the existence of subtraction. And this is the thing that doesn't work, right? Because there is no number such that 2 plus a is minus infinity. Right? Because maximum of 2 and a is always at least 2. So it cannot be minus infinity. So we don't have an additive inverse. However, if I ask you for a multiplicative inverse, then that's actually fine, right? So 0 is the neutral element of multiplication. So the a plus minus a is 0. A times minus a is 0, right? Because the multiplication is just the classical addition. So the multiplicative inverse exists. And the distributivity of multiplication over addition, well, that's just distribution. A times b plus c is, in classical notation, a plus maximum of b and c, which is the same as maximum of a plus b and a plus c. And so that gives us the distributivity. Okay. So we now know that these things are semi-fields. In fact, is this clear? So the second property is that these two semirings, the max plus semiring and the min plus semiring, are actually isomorphic to each other by a semi-field isomorphism that just sends a to minus a. Right? So again, a simple exercise is to prove that this is true. So basically, the only thing that we need to prove is that this isomorphism, this bijection that sends a to minus a, will replace maximization by minimization. So what it means is that the maximum of P of A and P of B is maximum of minus A and minus B. But maximum of minus A and minus B is the same as the minus minimum of A. So that gives us the fact that this operation turns mean plus addition into max plus addition. And the same is true. Okay. So now we have this two semiring. So now I can tell you what is the tropical semiring. So the tropical semiring is either one or the other, depending on who you ask. Okay. So what happened in tropical geometry is that for many reasons, let's say for convenience reasons and for historical reasons and so on, well, we simply do not have a fixed convention on which of the two is called the tropical semiring. Okay. So depending on the application, it may be more useful to consider the max plus semiring or the min plus semiring. And since these two guys are isomorphic, you can just translate all results from max plus to min plus. So it doesn't matter. So when you are going to a talk about tropical geometry, what often happens is that at the beginning of the talk, the speaker will just tell you which convention do they use, and they will just stick to this convention throughout the talk. So I'm going to do the same. So I typically work in the max plus semiring. So I did all of my slides in the max plus, and this is what I'm doing. But if you prepare the min plus, you can just take every result and put the isomorphism on it. Okay. And at this point, you know, people, when they hear about this for the first time, have the following question. Well, okay, this is a nice algebraic structure, but why do you call it tropical? Right? So here is the explanation on why is this called tropical. So actually, the name tropical semiring was coined by a few French computer scientists in order to honor a Brazilian computer scientist, Imre Simon. And Imre Simon was using the semirings in the study of regular languages in fundamental computer science. So he made a lot of advancements in this area. And Imre Simon was working in Brazil, in Sao Paulo. And Sao Paulo is located just at the Tropic of Capricorn. And this is why this French computer scientist decided to call this the tropical semiring. So tropical semiring is essentially a semiring from Sao Paulo. And you know, the name is very catchy, so we are not used. So let me recall that our aim for this lecture is to do some sort of algebraic geometry over this tropical scenario. So in order to do algebraic geometry, it would be good to have a notion of a polynomial, right? So how do we define the polynomial over the tropical scenario? Okay, so what is a polynomial? Well, a polynomial is simply a formal expression that looks like. So it's a formal expression that looks like a polynomial. It's just that we use the tropical notation. Okay, and here these exponents are natural, like for the usual polynomials. These coefficients are real numbers. Okay, so that's not the formal expression. And now what we can do with this formal expression? Well, we can associate as from in the standard geometry, right? We have a polynomial, so with the polynomial we can associate a polynomial function, right? So what is the polynomial function associated to this tropical polynomial? Well, it's simply the function that we get by interpreting these symbols as operations, right? So this is the function that is associated with the polynomial. And as you can see, there are a few technicalities here, right? So, you know, if you want to have a nice set of polynomials, there is this special polynomial called the zero polynomial. So there is the zero polynomial that has like an empty support, and P is non-zero if its support is non-empty. But for this talk, every polynomial will be non-zero to simplify things. And you can also note that, well, this thing is supposed to live in the tropical scenario, but here I define this function only over the reals. So I skip minus infinity. And this is what we very often do in tropical geometry, that we first do the results without minus infinity, and then if you need them, we will add it later, right? So in this talk, for simplicity, minus infinity will just disappear. So everything be over the. So in particular, my tropical polynomial function will only be defined over the real. Are there any questions? If not, then, well, let us do an example, right? So an exercise. So let us try to draw some tropical polynomial functions. Okay, so here I have two tropical polynomials, and I ask you to draw them. So let us see. So just let me recall. So what is this? So this tropical polynomial, when I interpret it as a function, is a maximum of 3 terms, right? So 3 terms here, 0, 2 times x, and minus 2 times x to the 3. So here I have a maximum of 3 terms. So the first term is 0, the second term is 2 plus x, and the third term is minus 2 plus 3x. Okay? So this tropical polynomial function is actually a maximum of 3 affine functions. Yeah? So when I draw it, what will happen? Well, I will have 3 segments, right? And actually, this 3 segments will look like this. So let us look at this Q1 term. So if my x is very, very small, then the maximum will be 0, right? So for x sufficiently small, the dominating term is the 0 term. And then as x equals to minus 2, what is going to happen is the maximum of 0 and 2 times x is going to be the same. So now after minus 2 is the second term that starts to dominate. And then when x reaches 2, and suddenly the second term and the third term coincide. And from then on is the third function that starts to dominate. Is this fine? I was solving all of these exercises myself, so you know it's very possible that there are mistakes. So if you see a mistake, tell me. Okay, so we see that this tropical polynomial function is actually, well, piecewise affine, increasing, right, and convex. Good. So what happens to the other function? So the function P2, well, it has the same three terms, but I added a fourth term, right? I added this term right here, -1 plus 2x. And now if you draw this -1 plus 2x line, this is this double thing here, then what happens is that this term is never the dominating term. Right? Maximum is never achieved on this term. Just in the signs. Okay, so what is the conclusion? Well, the conclusion is that these two p's are different polynomials. However, they define the same polynomial function. So a tropical polynomial is not uniquely determined by this function. And moreover, as we have just said, these functions are piecewise affine, continuous convex. And now, if you you prepare the mean plus savouring, then once you flip them, it will turn out that they would be increasing and concave instead of convex. Right? So this is how the math works. Okay. So that's an example. So we have just seen in this example that the tropical polynomial function is piecewise affine. We have seen this in for univariate polynomials, but this is true also for multivariate polynomials, right? Because what is a multivariate tropical polynomial? Well, it's, as we have discussed, it's some kind of a maximum of affine functions, just in multiple dimensions. So we will now try to formalize this. And by formalize this, we will try to give a description of the pieces of this function, right? So the function is piecewise affine, and we would like to describe what are the pieces. So to formalize this, let me just recall you the notion of what is a polyhedron. So a polyhedron is a set in Rn which is defined by closed affine inequalities. It's a set that you can write in this form. There are some affine inequalities and some affine equalities. And the face of a polyhedron is obtained by taking some inequalities and turning them into equalities. So this is a simple example. So this is a square, right? So the square is described by 4 inequalities. So 1, 2, 3, and 4. And now what is a face? Well, a face is obtained by taking an inequality and turning it into equality. So for instance, this segment is a face that I obtained by turning this inequality into equality, and this vertex is a face obtained by taking 2 inequalities and turning them into equality. So a square is a polyhedron with 4 faces of dimension 1. So these are the edges of the polyhedron, and 4 faces of dimension 0. These are the vertices. And now we can formalize how a tropical polynomial is piecewise affine. Okay. So the tropical polynomial basically decomposes the space into polyhedral cells, and on each of these cells, it is an affine function. And now we are going to try to describe this for. So we fix a tropical polynomial like this. And now, given a point x in R and a multi-index alpha, we will say that this index is dominating at x if the maximum is achieved by this index. Right? So for every point x, there is some number of terms that achieve the maximum, right? Maybe 1, maybe 2, maybe 3, maybe blah, blah, blah. And I will call this terms dominating at x. And now we do the reverse. So now, if we are given a non-empty subset of monomials, of these alphas, then you denote by the CI the set of all points for which the indices are simultaneously dominated. So the cell of I is the set of all x's such that for every alpha in I, the alpha is dominated. Right? So again, given x, there is some set of dominating terms. So we can reverse it and say, okay, given some set of terms, there is a set of x which are dominating of them. And now a simple proposition is that each of these CIs is a potentially empty polyhedron, and the function Px is affine on every non-empty cell. And moreover, the union of the cells is tubular. Okay, so is this clear that this thing is a polyhedron? And if yes, what are the inequalities? Or equalities?
There are the inequalities that we
Well, so let us recall, yeah, that this thing is a maximum of affine functions, right? So if I'm saying that this is supposed to be equal to the maximum, so how can I describe it? Well, this is supposed to be greater or equal than every other term, right? So this is an affine inequality. Okay, and if I have multiple guys that are supposed to be dominating, then I have to set them to be equal. So between themselves, they should be equal, and they have to be greater than everybody else. Right? So that gives me a set of equalities and inequalities. So this is why the thing is a polyhedron. And well, the function P of x is affine on every such polyhedron. Well, just by this definition, I just defined that that x is equal to once. Okay, so let us do another exercise. So in this exercise, we want to draw all of the polyhedra CI for the bivariate linear tropical polynomial that is given by this expression. Okay, so let us walk through this example. So here we have three terms. So since we have three terms, there is how many possible subsets of indices? Well, in theory, 8, right? However, an empty set never occurs. So in fact, we have 7. And because at every point there is at least one dominating index, so there is no point for which the set of dominating indices is empty. So it's not 8, it's 7. Okay, so we have 7 possible polyhedral cells, and some of these polyhedral cells may be empty, some may be non-empty. So in this example, all 7 cells will be actually non-empty. So let us try to see what are these cells, right? So we get 7 polyhedra. So for the simplicity of notation, right? So I will here denote these monomials. So this is the monomial with multi-index 0, 0, right? This guy has multi-index 1, 0, and this guy has multi-index 0, 1. Right? So this is my set of multi-indexes A, B, C. Okay, so let us look. So what is the polyhedron given by the cell of A? So this is the cell of 0, 0. So as we just discussed, well, is the set of all points such that 1 is greater than 2 plus x1, and 1 is greater than minus 3 plus x2. So on these points is this first term that dominates. Okay, so when you solve this, you get x1 smaller than minus 1 and x2 smaller than 4. So this is precisely this polyhedron here. Right? So here x1 is -1, here x2 is 4, and this polyhedron is the set of points on which the first term is the domain. So similarly, we can take the first two terms. So now what is the set of all x's so that the first two terms dominate simultaneously? Well, first of all, they have to be equal to each other. So 1 has to be equal to 2 plus x. And secondly, they have to be greater than all other terms. So 1 has to be greater than -3 plus x2. So we solve this and you get x1 equals to -1 and x2 smaller than. So going back to this picture, well, we get this segment right here. Right? So this is x1 equals to -1 and x2 smaller. And you can do this for all of the other. And you get this picture. So on this fragment, it's the first term that dominates. On this fragment is the second term that dominates. On this fragment is the third term that dominates. Now on this segment, we have two dominating terms AB. On this segment, we have two dominating terms AC. And on this segment, we have two dominating terms G and C. And at this point, every term is equal. So they are all three dominating. Is this fine so far? Any questions? Okay. So this is the space decomposition given by a tropical linear function. And now we want to say that this space decomposition actually has some sort of a special structure that we actually kind of see from this picture, right? So what happens is that, well, if I have a cell on which A dominates and a cell on which C dominates, then in between them, it's A and C who dominate. Right? That may sound like a simple observation, but geometrically it's actually quite interesting. Because what it means is that this decomposition of space has some special geometric structure, namely, it is a polyhedral complex. So what is a polyhedral complex? A polyhedral complex is a collection of polyhedra that has the following two properties. First of all, if I have two polyhedra in my collection, then the intersection of them is a common face, right? Well, provided that it's like non-empty. Right? So the intersection is supposed to be a common face. And the second property is that if you have a polyhedron in K, then all of its faces are also. Okay. So let us see what is the relationship to the tropical polyhedron. Well, so I claim that this collection of cells that we have just discussed forms a polyhedral complex. And more precisely, what we have is that the set F is a face of C if and only if F of the form C of J for some bigger J, right? So if I have a cell, then a face is actually given by having more dominating terms. And for any Hij, we have that the intersection of two polyhedra, described by I and J, is actually the cell of the union. Right? So what it means is that if I take a point for which both indices from I and indices from J are dominating, then the indices from the union are dominating. Right? So it's a simple exercise to prove this. The proof is just by turning the definitions on. Okay, so now let me show you that this actually imposes some conditions on this polyhedral complex. So here is the comparison. So on the left-hand side, we see what we have seen before. Right? So this is a space decomposition given by a tropical linear function. And on the right-hand side, we see something that looks similar. And now let me try to convince you that there is actually a big difference between this picture and this. So the big difference is that this on the left is a polyhedral complex, and the thing on the right is not. So why is the thing on the right not a polyhedron?
What exactly are you draw it as a picture? What exactly are you?
Well, no, the polyhedron is exactly what you see. That's polyhedron, that.
Yeah, but what about the segments?
Okay, yeah, that's a polyhedron, that's a polyhedron. That. You can just take the finest refinement of this thing. And you can put a vertex. I allow you to put a vertex here, a vertex. So why is this not a polyhedron? Yeah.
They mentioned that there must exist a point where every polyhedral is joined, so the complex contains every polyhedral. So, for example, if this line would have been drawn at the intersection of the others, then you could define a point where every polyhedral has a joint, so to say. I don't know if this goes in the right direction, but this is at least, it seems more well defined.
So, actually, the reason let us look at this figure. This so a face of this guy is this, right? So that's the face of this polyhedron on the top. And now we see that the intersection of this polyhedron and this polyhedron is not a common face, because the intersection is just this far. But the face of this guy is the stronger part. So the intersection of these two things is not a common face.
Technically, couldn't you just solve it by adding these segments? That's what you draw out there.
No, that's the point. No. If you say that this is a polyhedron in my collection, and this is a polyhedron in my collection, you still didn't solve the problem. Let me just because this thing is still not a base of this. So the intersection of these two things is that, but this thing is not a base of this bigger guy. However, you try to decompose. Because a phase is a geometric thing. A phase of this is this whole thing.
So, sorry, could you go back to the definition of polyhedral complex? Did you demand that the intersection is phase?
It's a common phase.
Oh, I see.
It's a common phase, well, provided it's not. You can say another name to say this a phase. Right? But it's supposed to be a common phase. But the intersection of these two things is not a common. So the fact that tropical polynomials actually divide space into a polyhedral complex, it imposes some structure. It's just not just some arbitrary division of a space into polyhedra, right? It's a very nicely structured division of space into polyhedra. Yeah.
But does this also imply that the only legal polyhedral complex would be one where there's always one point where all complexes are joined? Because in this case, you would avoid your problem by essentially drawing a line that would also intersect the intersection of the others.
Yeah, so, well, there are many ways of avoiding this problem, but so for instance, you can just take this line and prolong it here in this direction. And now everything will be fine. Okay. Or you can draw this line and prolong it in this direction, and also it's parallel to this. And it will also be fine.
Would it also be possible to just draw this last line at a slight angle, so that it's not a straight line, but basically would that work as well?
But sorry, so the problem is here. Right?
Exactly. So if you draw the line to the left of this at a slight angle, so that it's not straight anymore, exactly like this.
So if you take this and you draw this like this, yes, that's true.
Okay, so because then basically it's separate things.
Yes, right. Okay, so if you have understood this so far, then that's great because you will be ready for the lecture of tomorrow. But today, I wanted to tell you about the dual viewpoint on this polyhedral complex that we often use in tropical geometry. But this is when things start to get a bit abstract. Okay, so the dual viewpoint on this decomposition relies on the notion of Newton polyhedra, or rather Newton polyhedra. So now we will say that given a tropical polynomial, its Newton polytope is the convex hull of the multi-indices. Okay? And here is the definition of what it means to be a convex hull, right? So you take all of these multi-indices and you take basically the non-negative combinations such that the weights come out. So you may have seen this notion in the classical algebraic geometry, because if you have a standard polynomial, people also often discuss the Newton polytope of a standard polynomial, and this is the exact same definition, right? Because as you can see, well, in this definition, we do not actually use the coefficients of the polynomial, right? So it only depends on this set of multi-indices. So it doesn't matter if you take tropical or standard, it's just the same thing. Okay. So is this notion okay? Okay. So in tropical geometry, we also like to use the notion that actually uses the coefficients. So here we will talk about the extended Newton polytope. So an extended Newton polytope takes into account stretch. So how will you get the extended Newton polytope? Well, it will be in one dimension higher. So your multi-indices live in Rn, and my extended Newton polytope will be Rn plus 1. And how do I get it? I take this collection of points. So I take alpha as my multi-index, and then add C alpha. And then I take the convex hull of all of this. So, well, it is useful to think about it this way. So you have your Newton polytope, or rather the collection of points of your monomials. So they are in Rn. And then you add one more dimension, right? And then you take this point, and every point you rise it to the height C alpha. So you put them up. Okay, you can also go down because it can be also negative. And then after you do this rising or elevating them, then you take the convex hull. Okay, and I will call this the extended. Yes.
Why are you restricting the set of exponents to natural coupled function numbers?
It's just for the presentation. Yes.
And the coefficients. So alpha is also natural then?
No, C alpha real. C alpha real, but yes, the exponent could be much Of course, when then we will talk about the relations with classical polynomials, then the coefficient exponent should be natural. But people often do this in actually long polynomials, so they take also the negative. So that's the notion of the extended Newton polytope. So I think I have an example. Right? So here is the univariate polynomial that we have seen before. So this is the one that has this term that never achieves the maximum. Right? Okay, so now let us draw the Newton polytope and extended Newton polytope. So since this is in 1D, the univariate, the Newton polytope is not that interesting, right? So the Newton polytope is just a segment between 0 and 3. Okay? But the extended Newton polytope is a little bit more interesting. So what are our monomials? Well, the monomials, multi-indices are 0, 1, 2, and 3. Right? And now we raise it to the proper heights. So the first one we raise to the height 0, the second to the height 2, the third to the height -1, and the last one to the height -2. So that's what we get. So this is 0, 0, 1, 2, 2 minus 1, and 3 minus 2. And now we take the convex hull. So this extended Newton polytope is a triangle in R2. And this point, 2 minus 1, has this interesting property that it is inside. So we have seen that this point, this never achieves the maximum, and now is inside. So that should tell us that there is something geometric going on between the two. Right? Okay, so let us now see what is going on. So in order to see what is going on, we have to define what is an upper phase. So now we have your extended Newton polytope. Okay, so it's a polyhedron, so it has some phase. But now, like this guy here has 3 faces of dimension 1 and 3 faces of dimension 2. But now I will look only at special faces, the faces that we call upper faces. So what is an upper face? So an upper face is obtained like this. So you have your additional dimension, right? So you raise your point to heights, and this is your additional dimension. And you imagine that you look at your polytope from above. Okay? So the faces that you see when you look at your polytope from above are called upper. Okay? So now, okay, that seems like a weird definition. What does it mean that your face is visible from above? So here is the formal definition. So the formal definition says that a face is visible from above if it maximizes a linear function of this particular form. So you put something on the first n coordinate and 1 on the last one. And that's the super formal definition, right? So the super formal definition is okay. So my face is supposed to be in dimension n plus 1. So let me split the coordinates. So, right, so it's described by first n coordinates and the last coordinate. And I say that this set of points is an upper face if there exists x in Rn such that this thing is satisfied, right? So when I look at the set of points that maximize this function, now I get my. Yeah.
Is there like a projection between the space of tropical polynomials up to the same graph and the space of extended Newton polytopes? Because there's tropical polynomials that have the same graph. There's the terms that don't dominate.
Yes, we will see this in a moment. Yeah. How this is work. Okay. So yeah, this definition may seem a little bit complicated when you write it like this, but the intuition is that you just look at it from above and this is what you see. Can I show this on an example, or do you want to discuss this more? So maybe let me just show this on this example. Right? So find the upper faces of this. So now if you just imagine this. So imagine that you are looking at the scene from above. What do you see? Well, you will see essentially this edge and this edge, right? Nothing else. So in particular, you see this vertex, and this vertex, and you don't see this vertex. Right? And you also don't see the space, right? Because you just look at it from the. Is this fine?
Once again, how you define above?
Yeah, so you place yourself. So this is this additional dimension that I added, and you literally place yourself, sufficiently high in this direction, and you look at this plane, and this is the geometric English. But the formal definition is that this is supposed to maximize.
So I don't understand why is an extra direction. I mean, you already have 2 directions. You have points in the plane, right? So I would just assume that you have like direction.
This was this was a univariate case. So my points were here on this line, and then I raised them to the proper heights. So my extra dimension is the y-axis. Okay. So if you place yourself sufficiently high on the y-axis and you look down on this triangle, then you only see this thing. Right? So that's the geometric intuition. So this triangle has three upper vertices, 0, 0, 1, 2, and 3, minus 1, and two upper edges, this one and this one. And now when you want to check this formal definition, you can say, well, okay, so let us look at this edge, 1, 2, 3, minus 1. So this edge maximizes the function 2y1 plus y2. Okay? And this vertex will maximize the function 3y1 plus y2. Okay? So you see that these functions have coefficient 1 on this last variable. Okay? And this point is not a part of any upper face, even though it is higher than this vertex, which is. So this is an upper vertex, this is not. Is this fine? Right? So if you, for instance, take this edge, then you can find a linear function that such that this edge maximizes this function. But the function that you are going to find is never having this coefficient equal to 1. Right? You can find such a function with -1, but not 2. So this is a low. Is this okay? Okay, and now, well, we want to present some connection between the decomposition that we have seen before and now the upper face. So there is a duality between the cell decomposition and the upper faces of this extended loop. So this duality has some technicality. Is that, well, some of the cells that we have seen in our decomposition, well, they can be empty, right? We can see that it's empty. But they can also be degenerated in a more subtle way, in the sense that your cell can be non-empty, but can be essentially covered by another cell. So there is this condition that Ci can be equal to Cj, even though J is strictly greater. So if you add more dominating terms, your cell should be smaller, right? Because more dominating terms should have more equalities. But it can happen that even though you added more equalities, your cell actually didn't shrink. So this is a sort of degenerate situation, which generically doesn't happen. So what makes it? But up to this detail, we have the following proposition: is that your cell of your space decomposition, if it is non-degenerate, then it gives you an upper face. Right? You just take the same set of indices, and the convex hull of this set of indices gives you an upper face of this extended Newton polygon. And conversely, every upper face of your extended Newton polygon comes from such a set. Okay, and an exercise for you is to prove this. And it's really some sort of a duality in the sense that the cell is exactly the set of linear functions that are maximized on the face. And this is why we get this one coefficient will correspond to C alpha plus. So this is an exercise to prove that if there is really a duality, so you look at a face, you look at the functions that are maximized on this space, so that gives you a cell. And if you have a cell, you can just look at the face defined by this point x, and this will be a single upper face of the extended.
Sorry, is this saying very geometrically that all decompositions in Rn are basically shadows of upper faces of polytopes in Rn, right?
But it's not the decomposition, it's the dual of the decomposition. That will be in the next slide. It's the dual. Okay. So this is the duality between the cells and upper faces. And this duality reverses inclusions and dimensions. So if you have that cell I is included in cell J, then on faces it goes the other way around. So the face J is included in face I. And the dimension of cell plus the dimension of face is equal to M. Okay, so maybe let us see this on our example. How does it work? So in our example, so remember that was just one variable, right? So my cell decomposition decomposes R. So this cell decomposition splits R into 5 non-empty polyhedra. So the cell of 0 is this guy, is -2, is -infinity -2. Then the cell of 1 is this guy. Cell of 2 is this guy. And there are these cells of 0, 1, and 1, 3, which give you this. Okay? So these are our cells of our space decomposition. And there is this one degenerate cell corresponding to the cell. Okay, and now I think that these cells are dual to the upper faces of this other picture. So here the upper faces are what? So, so this is an upper face corresponding to monomial to the multi-index 0. This is an upper face corresponding to the multi-index 1. This is the upper face corresponding to our multi-index 3. And this is the upper face corresponding to the multi-indices 1. And now I claim that there is a duality that reverses dimensions and inclusions, right? So for instance, if I take this face 1, 3, so here it is an egg, right? And if I look at cell 1, 3, it's a point. Right? So here the dimension is 1, here the dimension is 0, as it was supposed to be. If I look at this cell, so here the dimension is 1, and the face has dimension 0. That was supposed to be, and also the inclusions are reversed. So if I take, let's say, what can I take? I take face of 1 is included in face of 0, 1. Right? So now I should have that the cell of 0, 1, this one, is included in the cell of 1, which is this one. And that also. Okay. So we have this duality between, yes.
So Mateusz, you started with definition of face, which is very analytic. So you have the description polyhedron with qualities equations. And then after you use this implicitly definition of face, which is maximization of an affine function.
Yes.
So all they are equivalent?
Well, in the sense that, yes, they are equivalent in the sense that if you look at this set of points that maximize this, there is some inequality that is turned into equality. Okay, so we have this duality between cell decompositions and upper faces. So now let me finish by saying you one more viewpoint on this duality. So we had the duality in which I said, okay, you take your Newton polytope, you raise the points, and you take the convex hull, right? And you look at upper faces. So now we do the following. So you look at your polytope from above, and now you take these upper faces and you project them back on Rn. So what are you going to obtain that? So you take an upper face, F, then the projection on Rn, well, is just the set convex hull of only the alphas, right? So we forget the heights, we take the convex hull of only the alphas. So in particular, this projection of an upper face is a polytope inside your Newton polytope. Okay? So you go from the extended Newton polytope to the standard Newton polytope, and you get some polytope inside. Okay? And now I claim that this sort of preserves this duality in the following sense. So if I look at this collection of polyhedra that you obtain by projecting the upper faces, you get a polyhedral complex that will subdivide the standard Newton polytope. Okay? And moreover, this has this still preserves the combinatorial structure of this object in the sense that, well, F is a phase of Fi, then it is a form Fj smaller j and so on. So it preserves this duality, right? So now instead of looking at duality between a cell and an upper phase, I can look at the duality between a cell and the polytope that is inside my Newton. And geometrically, it's just by taking a projection. So a subdivision of a Newton polytope that is obtained in this way is called the regular subdivision. So the theorem about is the duality between cell decompositions and regular subdivisions of Newton. So I think that this answers your question, right? So the cell decompositions are the same things as the regular subdivisions of Newton polytopes, if you just think about them combinatorially. Okay, so so let me finish by showing you just this example. So here there is an exercise: draw the cell decomposition, the regular subdivision of this guy. So here you have like 8 terms. So drawing this cell subdivision may take a little while, right? Because there is quite a lot of polyhedra that could arise. But after you do this exercise, you get something like this. So that's your space decomposition of this polynomial. And then what will be the subdivision? The subdivision can be just from this picture. So in this subdivision, we have the duality. So a full dimensional cell will correspond to a point. Let me just give you this picture, right? So this cell corresponds to this point, this monomial here. This cell corresponds to this point. This cell corresponds to this point, and this cell will correspond to this point. So it reverses the dimension. So this cell here is connected to 1, 2, 3, 4 cells. And the corresponding point here is connected to 1, 2, 3, 4 corresponding points. So this is really just the dual graph. So we put the point inside each cell and we connect the points which are of the cells which are adjacent, and you get precisely this. And this is exactly what you would get if you take this, look at the extended Newton polytope, look at the upper faces, project them back. Okay. So the final exercise that we can do before tomorrow's lecture is proof that this thing on the left is regular, thing on the right is. And I think that this is the great place.